wanted to work through an example that involves both time dilation and length contraction. So in this particular example, we're imagining a spaceship that is passing by the Earth. We're going to imagine that there's an astronaut in the spaceship. We're going to imagine that there's an Earthling standing on the Earth. The astronaut in the spaceship is one reference frame in this problem. The Earthling on the Earth is another reference frame in this problem. We're told in this problem that the astronaut and the rocket are moving at 0.9, the velocity of light, with respect to the Earth. That also means that in the opposite direction, the Earth is moving with respect to the astronaut at 0.9 times the velocity of light. So the question asks for us to determine several things. We've got to determine the true length of the rocket. We've got to determine the time it takes the rocket to pass by a point on Earth, say the Earthling's location, as measured by the Earthling and as measured by the astronaut. And the other piece of information that we're given is the Earthling has observed the length of the rocket to be 75 meters. So let's take a moment and just step back and think from the frame of reference of the astronaut. Think from the frame of reference of the Earthling. Who sees the proper length? Who sees the contracted length of the spaceship? And who sees the measures the proper time of the rocket to pass the Earthling? And who seems the time dilated time for the rocket to pass the Earthling? Well, to answer those questions, let's start with who sees proper length, who sees contracted length. The astronaut is sitting inside the rocket. The astronaut is in the rocket reference frame. The astronaut sees the proper length of the rocket. It's going to be the Earthling who's seeing the rocket moving, who sees the contracted length of the rocket. So that's the proper length, contracted length. What about the time it takes the rocket to pass by the Earthling, as seen by the Earthling, as seen by the astronaut? In that case, it's the Earthling that sees the proper time, because the arrival of the nose of the rocket at the Earthling, the departure of the tail of the rocket from the Earthling, are measured at the same location in the Earthling's reference frame. They're measured at different locations in the rocket reference frame. And so it's the Earthling that measures the proper time between events, the arrival, the departure of the rocket, that occur at the same location. It's the astronaut that sees the time-dilated time, because the events of leaving the Earth, Earthling, arriving at the Earthling, are seen at different times. There's one thing that both the astronaut and the Earthling agree on, and that's the laws of physics. The law of physics that's relevant here is simply that the speed of the rocket, if you're watching from the Earth, or the speed of the Earth, if you're watching from the rocket, the speed is the ratio of the distance traveled divided by the elapsed time. So they both agree on that equation. Okay, to solve this problem, before I get on with calculating proper lengths and proper times and dilated times, I'm actually going to calculate an important quantity that we're going to use in those calculations. That's the Lorentz factor. So the Lorentz factor is going to govern things like the time dilation and the length contraction. And the Lorentz factor is determined by this speed. It's the speed of the rocket with respect to the Earth, or the Earth with respect to the rocket. The Lorentz factor, gamma, is equal to 1 minus v over c squared. That factor in parentheses, and then you take the square root and you take the inverse, so to the power minus 1/2. And we know the speed of the rocket with respect to Earth, or vice versa. And so we can plug in v over c. So it's going to be 1 minus 0.9 squared to the power of negative 1/2. And if you calculate that number, I got a value 2.29. Now we can go on and calculate the quantities that we're asked to figure out. We knew the contracted length. We want to figure out the proper length, and then we're going to calculate the dilated time and the proper time. So firstly, for the proper length, the relationship between the contracted length that's measured by the Earthling who sees the rocket moving, and the proper length that's seen by the astronaut who sees the rocket stationary, is this little relationship here. L0 is the contracted length, sorry, L is the contracted length, L0 is the proper length, and gamma is the Lorentz factor. Now, in this particular case, I know the contracted length. I want to figure out the proper length, so I'm going to rearrange this for L0. L0 equals gamma L, and I'm going to fill in the factor of gamma that I calculated, 2.29. Going to multiply it by the contracted length, 75 meters, and if I do that, I get a true length, 172 meters. So that's the length of the rocket as seen by the astronaut. That's the proper length of the rocket. Next part of the question. Next part of the question, we're going to calculate the proper time between for the rocket passing some point, say the location of the Earthling on the Earth. That proper time is measured by the Earthling on the Earth, because the arrival of the rocket at the Earthling, its departure from the Earthling, are occurring at the same location in the Earthling's reference frame. So the way we're going to calculate that is this law of physics, that the speed is equal to the distance traveled divided by the elapsed time. In this case, this is the speed of the rocket measured with respect to Earth. This is the distance the rocket's going to travel to pass the Earthling, which is the contracted length of the rocket. And this is the time it takes to pass the Earthling, which is the proper time that's measured by the Earthling. Now, in this particular case, we know the contracted length, we know the speed, we don't know the proper time. I'm going to rearrange this for the proper time. So the proper time will be the contracted length divided by the speed v. I know these two numbers, so 75 meters divided by 0.95 c, 0.90 c. And if I take 75 meters, divide it by 0.9 times 3 times 10 to the 8 meters per second. So I won't actually write that in. I got a value that for the proper time, that is 0.27 microseconds. That's a very short amount of time, because the speed of light is a very large number, 300 million meters per second. Now we want finally not the proper time, we just calculated that. We want the time dilated time that's measured by the astronaut to pass by. Well, one way we can do this calculation is again use the same law of physics, that the speed of a object is related to the distance traveled divided by the elapsed time. in this particular case, we know the speed again, and this is the speed of the Earth passing by the astronaut and the rocket. We know the distance traveled. This is the proper length of the rocket. We're trying to find out the elapsed time. And so if I rearrange this equation, I'm going to get the elapsed time, which is the dilated time, is going to be L naught over V. The L naught is the 172 meters. That was the proper length of the rocket. The V is still the 0.90 C. The astronaut sees the Earth moving with the same speed that the Earthling sees the astronaut moving. And if I divide one number by the other number here, remember I'm filling in 3 times 10 to the 8 meters per second, I get 0.64 microseconds. You see, this time here is more than 2 times longer than the proper time. It's the dilated time. It's been diluted by a factor, again, that is the Lorentz factor upstairs. And so that's a conclusion of our little problem involving length contraction and involving also time dilation. Solving that problem, the challenge, I think, is understanding, from these 2 observers in these 2 different frames, the astronaut and the Earthling, who's seeing the proper time, who's seeing the dilated time, who's seeing the proper distance length, who's seeing the contracted length. So that's the challenge. The formulas, the equations are simple and straightforward. We just use the formula for speed. We just use the formula for length contraction. We could have used the formula for time dilation involving the Lorentz factor.